Welcome to this walkthrough of LeetCode problem number 2035, partition array into two arrays to minimize some difference. In this problem, we'll explore an interesting challenge of splitting an array into two subsets to minimize the absolute difference between their sums. Let's dive in. The problem asks us to work with an integer array, nums, which always has an even length of 2*n. Our task is to split this array into two smaller arrays, each of size n, such that the absolute difference between the sums of these two arrays is as small as possible. The goal is to return this minimized absolute difference as a single integer. For example, if you are given an input array like 3, 9, 7, 3, you would calculate the partitions and determine the smallest absolute difference between the sums. The constraints ensure that n can range from 1 to 15, meaning the total array length can go up to 30. This makes finding an efficient solution critical. Let's take a closer look at how the problem works with an example. Consider the array nums equals 3, 9, 7, 3. Here, the size of the array is 4, so n equals 2. One way to partition the array is into 3, 9, and 7, 3. The sum of the first array is 12, and the sum of the second is 10. The absolute difference between these sums is 12, 10 equals 2, which is the smallest possible difference for this input. Similarly, for the input nums equals -36, 36, the array size is 2, so n equals 1. This means we split it into two arrays of size 1, -36, and 36. The sums are -36 and 36, resulting in an absolute difference of -36, 36 equals 72. These examples illustrate how the problem requires us to carefully evaluate partitions to minimize the difference. Now, let's examine another example to understand the problem further. Suppose the input array is nums equals 2, -1, 0, 4, -2, -9. Here, the array size is 6, which means n equals 3. One possible partition is 2, -1, -9, and 0, 4, -2. The sum of the first array is -8, and the sum of the second array is also -8. The absolute difference between these sums is -8 minus 8 equals 0. Since the absolute difference is 0, it cannot get any smaller, making this the optimal solution. This example highlights that the problem can involve both positive and negative numbers, and the solution must account for all possible partitions to ensure the absolute difference is minimized. To solve this problem effectively, we need to consider several important aspects. First, the array can have up to 30 elements, as 2*n can go up to 30 due to the constraint 1 equals n equals 15. This means that brute forcing through all possible partitions is computationally expensive, so we'll need to explore efficient techniques like combinatorics, subsets, or divide and conquer strategies. Additionally, we must handle edge cases such as arrays with all positive numbers, all negative numbers, repeated values, or very small arrays where n equals 1. These edge cases ensure that the solution is robust and performs well under different conditions. The problem challenges us to think critically about how to partition the array while keeping the absolute difference as small as possible. To solve the problem of partitioning the array nums into two equal-sized subsets to minimize the absolute difference between their sums, we first explore the brute force approach. This method involves generating all possible ways to split the array into two subsets of size n. For each partition, we calculate the sums of both subsets, evaluate their absolute difference, and keep track of the smallest difference found. However, this approach is highly inefficient because the number of combinations to consider grows exponentially with the size of the array. Specifically, for an array of size 2n, there are 2n combinations, which makes this method computationally infeasible for larger arrays. While straightforward in concept, this approach is impractical given the constraints of the problem. An optimized approach to tackle this problem is the meet-in-the-middle strategy. This method begins by splitting the array nums into two halves. The first n elements form the left half, and the last n elements form the right half. We then generate all possible subsets of each half and calculate their sums. This results in two lists, sum_left, containing the sums of all subsets from the left half, and sum_right, containing the sums of all subsets from the right half. Next, we sort one of these lists, such as sum_right, to enable efficient binary search. By iterating through each sum and sum_left and using binary search on sum_right, we can quickly find the closest matching sum that minimizes the absolute difference between the two subset sums. This approach dramatically reduces the computational complexity to n*2n/2, making it significantly faster and more scalable than the brute force approach. The meet-in-the-middle approach emerges as the most practical and efficient solution for this problem. A key reason for this choice is the size constraint of the array, which is 2n with n being as large as 15. Under these constraints, the brute force method becomes infeasible due to its exponential growth in combinations. By dividing the array into two halves, the problem size is effectively reduced, allowing us to handle subset sums more efficiently. Additionally, sorting one list of subset sums and utilizing binary search ensures that we can quickly identify the closest pair of sums to minimize the absolute difference. While the dynamic programming approach is conceptually possible, it remains less efficient and requires significant memory and computation, making it less practical for this problem. The meet-in-the-middle approach strikes a balance between computational efficiency and implementation complexity, making it the best choice. The meet-in-the-middle strategy is the optimal choice for solving this problem due to its balance of efficiency and practicality. By reducing the computational complexity from n*2n in the brute force approach to n*2n/2, it becomes scalable for the given constraints. The method's use of subset sums and binary search ensures that the absolute difference between the two subset sums is minimized within a reasonable runtime. Unlike dynamic programming, which can be memory-intensive and harder to implement, this approach remains straightforward while delivering significant performance gains. Overall, the meet-in-the-middle strategy effectively addresses the problem's requirements, making it both an elegant and efficient solution. The goal of this problem is to partition an array nums of size 2*n into two subsets of size n such that the absolute difference between their sums is minimized. This is a challenging optimization problem because we need to explore all possible ways to split the array while keeping the difference as small as possible. To solve this efficiently, we use a strategy called the meet-in-the-middle approach, combined with bit manipulation. First, we divide the array into two halves, left, which contains the first n elements, and right, which contains the last n elements. This reduces the complexity of the problem, as we can focus on smaller subsets. Next, for each half, we calculate all possible subset sums for subsets of sizes ranging from 0 to n. Using bit manipulation allows us to efficiently generate the 2n possible subsets for a half. These sums are then stored in a dictionary, where the keys represent the size of the subset, and the values are lists of sums corresponding to that size. This organization will make it easier to pair subsets later. Finally, we sort the subset sums for each size, setting up the foundation for the next step of minimizing the difference. Sorting the subset sums is critical because it allows us to efficiently find the closest pair of sums between the two halves. With the sums organized, we compute the total sum of the array, total_sum, and iterate through all possible subset sizes, k, from 0 to n. For each subset sum from the left half of size k, we look for the closest subset sum from the right half of size nk that minimizes the absolute difference. The formula we use is abs, total_sum, 2*, left_sum plus right_sum. Here, left_sum and right_sum represent the sums of the selected subsets from the left and right halves, respectively. The subtraction and doubling in this formula ensure that we're effectively comparing the two partitions of the array. To find the closest right_sum efficiently, we use binary search on the sorted subset sums of the right half. This reduces the time complexity of this step significantly compared to a brute force approach. Throughout this process, we keep track of the smallest absolute difference encountered using a variable min_diff. Once all possible subset sizes have been considered, the value of min_diff is returned as the result, representing the minimum sum difference achievable. Splitting the array into two halves is a key optimization, as generating all subsets for the original array would result in 2n subsets, which is computationally infeasible for large n. By dividing the array into two halves, we reduce the problem size to 2n subsets for each half, which is manageable for values of n up to 15. Additionally, sorting the subset sums enables us to use binary search to find the closest complementary sum in the other half. This drastically reduces the complexity of searching from O2 to the power of n to O log 2 to the power of n for each subset sum. The formula abs, total underscore sum 2 asterisk, left underscore sum plus right underscore sum, is central to balancing the two partitions. The term 2 asterisk, left underscore sum plus right underscore sum, represents the combined sum of the selected subsets, while subtracting it from total underscore sum ensures that the remaining elements are also balanced. This insight ensures that we're minimizing the absolute difference effectively. To support this algorithm, we use a dictionary to store subset sums, with the keys representing subset sizes and the values being lists of sums. This structure allows us to efficiently organize and retrieve sums by their sizes, which is crucial for pairing subsets during the optimization process. The reason we use a dictionary for subset sums is to organize them by their sizes, enabling efficient pairing of subsets from the two halves. This structure makes it easy to retrieve and manage sums for specific subset sizes. Additionally, sorting the subset sums is essential for enabling binary search, which is used to find the closest complementary sum in the other half. Without sorting, finding the optimal pair would require a brute force comparison, which is computationally expensive. With these optimizations in place, the time complexity of the algorithm can be analyzed. Generating subsets for each half takes 2 to the power of n asterisk n, due to the need to compute all possible subsets and their sums. Sorting these subsets takes n asterisk 2 to the power of n asterisk log 2 to the power of n, as we sort the sums for each subset size. Finally, the binary search step, which is performed for each subset size, also takes n asterisk 2 to the power of n asterisk log 2 to the power of n. Combining these steps, the overall time complexity is 2 to the power of n asterisk log 2 to the power of n. The space complexity is proportional to the storage required for the subsets, which is 2 to the power of n asterisk n, for each half. These bounds make the algorithm efficient for moderately sized inputs, such as n equals 15. It's important to consider edge cases to ensure the algorithm works correctly in all scenarios. If all elements in the array are the same, the difference is 0 because the array can be split into two identical halves. For arrays with very large or very small integers, it's critical to ensure calculations do not overflow. While Python handles large integers natively, other programming languages may require special data types to avoid overflow errors. Arrays containing 0 or negative elements are also handled correctly by this algorithm, as the absolute difference formula remains valid regardless of the values. These considerations ensure that the algorithm is robust and can handle a wide variety of input cases. By addressing these edge cases, we can confidently apply this solution to real-world problems or competitive programming scenarios. To solve the problem of partitioning an array into two arrays that minimize the absolute sum difference, we start by importing the combinations function from itertools and defining our solution class. Inside the minimum difference method, we calculate the total sum of the array and determine a target value, which is essentially half of the total sum. This target will guide us in balancing the two partitions as closely as possible. Next, we split the array into two halves, left and right. The idea here is that we will compute all possible subset sums for each half separately. To achieve this, we define a helper function called generate_sums. This function takes an array, calculates all possible sums for subsets of each size, and stores these sums in a dictionary where the keys represent the subset size. For instance, if a subset has size k, the corresponding sums are stored under key k in the dictionary. We then apply this function to both the left and right halves of the array, obtaining all their possible subset sums. At this stage, we initialize a variable min_diff to infinity, which will help us track the smallest difference we can achieve as we explore different subset combinations. Now, we iterate through all possible subset sizes from 0 to n, where n is half the length of the original array. For each size k, we retrieve the pre-computed subset sums for the left half of size k and for the right half of size n k. These subsets are sorted to facilitate efficient comparison. Using a two-pointer approach, we aim to find the pair of sums, one from the left set and one from the right set, that gets as close as possible to the target value. The target here is derived from splitting the total sum into two balanced halves. Within the while loop, we calculate the absolute difference between the combined sum of the current pair and the target. If this difference is smaller than the current min_diff, we update min_diff. Depending on whether the current combined sum is less than or greater than the target, we adjust the pointers to explore other potential pairs. Specifically, if the sum is less than the target, we move the left pointer forward to increase the sum. If the sum exceeds the target, we move the right pointer backward to decrease the sum. Once all possible combinations have been evaluated, we return twice the minimum difference as the result, effectively providing the smallest achievable difference between the two partition sums. Here, we begin by defining the Java solution for the problem. The method minimum difference takes an array of integers, nums, as input. First, we calculate the total number of elements in one half of the array, n, since the goal is to partition the array into two subsets. We also compute the total sum of all elements and determine the target, which is half of the total sum. This target will help us minimize the difference between the sums of the two partitions. Next, we split the array into two halves, left and right, using the arrays.copyOfRange method. To explore all possible subset sums for both halves, we use a helper function generateSums, which returns a map where the key represents the subset size and the value is a list of all possible sums for subsets of that size. With these in place, we initialize mindiff to the maximum possible value, which we will update as we process the subsets. Finally, for each subset size k, we retrieve the corresponding sums for the left and right halves, sort them, and prepare to use the two-pointer technique for efficient comparison. Now, we focus on the two-pointer technique, which helps find the closest sum to the target efficiently. For every subset size k, we iterate through the sorted lists of subset sums from left set and right set. Using two pointers, I starting at the beginning of left set and j starting at the end of right set, we calculate the sum of the current pair of elements. The absolute difference between this sum and the target is calculated, and mindiff is updated to the smaller of its current value or this difference. If the current sum is less than the target, we increment I to explore larger sums in left set. Otherwise, if the sum is greater than or equal to the target, we decrement j to explore smaller sums in right set. This process continues until all possible sums for the current subset size have been evaluated. Once all iterations are complete, we return mindiff *2, as the problem's final result requires considering the total difference rather than the difference from half the total sum. The generateSums method is supported by the generateCombinations helper function, which uses recursion to compute all possible subset sums for a given subset size. This function takes an array ARR, the current index IDX, the size of the subset k, the cumulative sum current sum, and the result list to store the sums. If the required subset size k becomes 0, the current sum is added to the result list, and the recursion terminates for this path. Otherwise, we iterate through the remaining elements of the array starting at the current index. For each element, we recursively call generateCombinations, moving to the next index, decreasing the required subset size by 1, and adding the current element to the cumulative sum. This ensures all combinations of size k are explored. The results are collected in the map by subset size in the generateSums method, which is essential for efficiently calculating the subset sums used in the main algorithm. To begin solving the problem with the given input array nums equals 1, 2, 3, 4, 5, 6, we first calculate the necessary parameters. The total length of nums is 6, so we divide it into two halves, each of size 3. This gives us n equals 3, and the total sum of the array is 21. Our goal is to split the array into two subsets such that the absolute difference between their sums is minimized. To achieve this, we aim for each subset to have a sum close to half of the total sum, which is target equals 10. Next, the array is split into two halves, left equals 1, 2, 3, and right equals 4, 5, 6. From here, we generate all possible subset sums for both halves. For left, we calculate sums for subsets of sizes 0, 1, 2, and 3, resulting in 0, 1, 2, 3, 3, 4, 5, and 6, respectively. Similarly, for right, we generate 0, 4, 5, 6, 9, 10, 11, and 15 for subsets of sizes 0, 1, 2, and 3. These subsets will help us identify combinations with minimal differences. Now we move to minimizing the sum difference using the generated subset sums. We initialize min_diff to a large value, infinity, and evaluate every subset size k from 0 to 3. For k equals 0, we consider subsets with 0 elements, left_set equals 0, and right_set equals 15. The closest pair gives an absolute difference of 0 plus 15, 10 equals 5, so we update min_diff to 5. For k equals 1, subsets of size 1 are compared, left underscore set equals 1, 2, 3, and right underscore set equals 9, 10, 11. The closest pair results in 3 plus 9, 10 equals 2, updating min underscore diff to 2. For k equals 2, subsets of size 2 are evaluated, left underscore set equals 3, 4, 5, and right underscore set equals 4, 5, 6. The pair with the smallest difference gives 5 plus 5, 10 equals 0, and min underscore diff is updated to 0. At k equals 3, no better difference is found. Ultimately, the smallest possible difference is doubled to give the final result, which is 0. Now consider a second example where the input array is nums equals 7, minus 3, 2, 5, minus 4, 1. Following the same process, we calculate the parameters. Here, n equals 3, the total sum of the array is 8, and the target sum for each subset is 4. We split the array into left equals 7, minus 3, 2, and right equals 5, minus 4, 1. Next, we generate subset sums for each half. For left, the sums are 0, for size 0, 7, minus 3, 2, for size 1, 4, 9, minus 1, for size 2, and 6, for size 3. For right, the corresponding sums are 0, for size 0, 5, minus 4, 1, for size 1, 1, 6, minus 3, for size 2, and 2, for size 3. These subsets provide us with the necessary combinations to minimize the difference between the two subset sums. Using the subset sums from the previous step, we minimize the difference. Starting with min underscore diff equals infinity, we evaluate each subset size k from 0 to 3. For k equals 0, the closest pair of sums gives an absolute difference of 0 plus 2 for equals 2, updating min underscore diff to 2. For k equals 1, the closest pair results in 2 plus 1 for equals 1, reducing min underscore diff to 1. At k equals 2, the smallest difference is achieved with a 4 plus 1 for equals 0, and min underscore diff is updated to 0. At k equals 3, no better result is found. Doubling this smallest difference gives the final result, which is 0. Let's now explore a third example with the input array nums equals 10, 20, 15, 25. Here, the length of nums is 4, so n equals 2. The total sum of the array is 70, and the target sum for each subset is 35. The array is split into two halves, left equals 10, 20, and right equals 15, 25. We then generate all subset sums for these halves. For left, the sums are 0 for size 0, 10, 20 for size 1, and 30 for size 2. For right, the sums are 0 for size 0, 15, 25 for size 1, and 40 for size 2. With these subsets, we can now identify the combinations that minimize the difference between the subset sums. To minimize the difference, we evaluate the subset sums for each size k. For k equals 0, the closest pair yields an absolute difference of 0 plus 40, 35 equals 5, so we set min underscore diff equals 5. For k equals 1, the closest pair gives 20 plus 15, 35 equals 0, and min underscore diff is updated to 0. At k equals 2, no better difference is found. Doubling the smallest difference results in the final output, which is 0. To begin with, the time complexity of this solution can be analyzed step by step. First, we split the input array nums into two halves called left and right. Since this operation involves iterating through the array once, it takes n time, where n is the size of the input array. Next, we generate all possible subset sums for each half using the generate underscore sums function. For any array of size n/2, there are 2 n/2 possible subsets. Generating these subsets and calculating their sums requires 2 n/2 n/2 time for each half. Since there are two halves, this step contributes a combined time complexity of 2 n/2 n. Additionally, the subset sums are sorted for each subset size. Sorting a list of size 2 n/2 takes 2 n/2 log 2 n/2, which simplifies to 2 n/2 n/2. Even though sorting is repeated for all subset sizes, the dominant term remains 2 n/2 n. Now, let's focus on the step of finding the minimum difference. For each subset size k, we iterate through the subset sums in left underscore sums, k, and use binary search to find the closest value in the corresponding right underscore sums, nk. Since binary search on a sorted list of size 2 caret n/2 requires O log 2 caret n/2 time, which simplifies to O n/2, this step involves O n asterisk 2 caret n/2 asterisk n/2 operations in total when considering all subset sizes. Simplified, this becomes O n squared asterisk 2 caret n/2. Combining all these steps, the dominant contributor to the overall time complexity is the generation and sorting of subset sums, which takes O 2 caret n/2 asterisk n. Thus, the overall time complexity of the solution is O 2 caret n/2 asterisk n. On the space complexity side, the storage requirements for subset sums dominate. Specifically, the generate underscore sums function stores all subset sums for both halves, requiring O 2 caret n/2 asterisk n space. Additionally, when generating subset sums, temporary storage is used for creating combinations, which requires O k space for a subset of size k. However, this space usage is negligible compared to the storage required for all subset sums. As for sorting the subset sums, since sorting can be performed in place, it does not require any additional space beyond the already allocated storage. Therefore, the overall space complexity is determined by the storage of subset sums, which is O 2 caret n/2 asterisk n. Comparing this optimized approach to a brute force method is insightful. A naive solution would involve generating all 2 to the power of n subsets of the input array, dividing them into 2 groups, and calculating their sums to find the minimum difference. This would result in a time complexity of O 2 to the power of n asterisk n, and a space complexity of O 2 to the power of n. By splitting the array into 2 halves and focusing on arrays of size n/2, the optimized approach reduces the time complexity to O 2 caret n/2 asterisk n, and the space complexity to O 2 caret n/2 asterisk n, which is a significant improvement for large input sizes. Finally, let's analyze the best, average, and worst cases. Regardless of the specific values in the input array, the time and space complexity remain the same across all cases. This is because the algorithm always computes all possible subset sums for both halves and searches for the minimum difference across all combinations. To mathematically validate the big O notation, consider that the number of subsets of an array of size n/2 is 2 caret n/2. Generating each subset takes O n/2 time, and sorting the subset sums requires O 2 caret n/2 asterisk log 2 caret n/2. Combining these, the dominant term for time complexity is O 2 caret n/2 asterisk n. Similarly, the space complexity is proportional to the number of subsets and their storage, leading to O 2 caret n/2 asterisk n. This formal analysis confirms that the optimized approach is both efficient and scalable compared to the brute force alternative. Here are some common mistakes to watch out for when tackling this problem. The first issue is failing to consider all possible subset sizes. The problem requires evaluating subsets of every size up to n, and overlooking this can lead to incorrect results. Another common pitfall is relying on an inefficient brute force approach. While generating all possible subsets of size n may seem straightforward, this quickly becomes computationally expensive, especially for larger inputs, leading to time-limit-exceeded errors. Additionally, it's important to handle edge cases carefully. For example, arrays with repeated elements or arrays where all elements are identical can produce unexpected results if not accounted for. Finally, improper use of binary search is another frequent error. If the binary search result goes out of bounds, such as finding a value smaller than the smallest or larger than the largest subset sum, it can cause runtime errors. Careful handling of these scenarios is critical for a robust solution. Floating point arithmetic errors are another potential issue to avoid. Using floating point numbers for some calculations can introduce precision inaccuracies. Fortunately, this problem can be solved entirely with integer arithmetic, which avoids such complications. Now, let's discuss some key insights relevant to interviews. The divide and conquer principle is central to solving this problem efficiently. By splitting the array into 2 halves, calculating all possible subset sums for each half, and then using binary search to find the closest sums, we can leverage the meet-in-the-middle approach for optimal performance. Pre-computing and sorting subset sums for smaller arrays is another powerful optimization. This allows binary search to efficiently find the best partition in logarithmic time. Additionally, modular thinking is highly valuable here. Breaking the problem into smaller, manageable pieces demonstrates strong problem-solving skills. Finally, be ready to articulate the trade-offs between different approaches, such as the space versus time complexity of brute force methods compared to optimized solutions. This problem also shares similarities with several related problems that can help you build foundational skills. For instance, LeetCode 416, partition equals subset sum, is a simpler version of subset partitioning, while LeetCode 698 focuses on dividing an array into k subsets with equal sums. LeetCode 494, target sum, involves dynamic programming to solve a subset sum variation, and LeetCode 805, split array with same average, introduces similar partitioning challenges. These problems are excellent for sharpening your understanding of subset sum techniques. Now, let's discuss alternative approaches. Dynamic programming is one option where you calculate whether a subset sum is possible for each value up to half the total sum. This avoids explicitly generating all subsets but may require significant memory for larger inputs. Another approach is the meet-in-the-middle method. By splitting the array into two halves and using binary search on pre-computed subset sums, this method achieves faster performance while trading off some additional space. Each approach has its strengths and weaknesses, so understanding their trade-offs is essential. Branch and bound is another alternative for solving this problem. This is a recursive backtracking approach that prunes unpromising partitions to reduce the search space. It can be more efficient than brute force, as it avoids exploring every possible subset, but it is also more challenging to implement correctly. This method requires careful pruning conditions to ensure efficiency without compromising accuracy. However, it's worth noting that while branch and bound can be effective for smaller inputs, it may still be slower than the meet-in-the-middle approach for larger arrays. Ultimately, the choice of approach depends on the problem constraints and your familiarity with these techniques. Being able to justify your approach and discuss the trade-offs in terms of time and space complexity is a valuable skill, particularly in an interview setting. Great job completing this walkthrough of LeetCode problem number 2035. We covered the problem requirements, the algorithmic approach, and its complexity. Remember, subset sum problems are a critical aspect of optimization challenges, so keep practicing. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!